Swayam Prabha. Digital India. Educated India.
We are going back. I know you have learnt all the advanced stuff, but we still probably need to get some clarity on how the method works at its core. Right? So, where is the echo coming from? Yeah, now it is okay. Yeah. So, that is what we are trying to do now. So, the general governing differential equation for overall governing differential equation for a dynamical system is mu double dot, where u is the displacement. So, this will be acceleration plus, I think this should have been written as Cu dot plus Ku. I am sorry for that. It should have been Cu dot plus Ku. This u dot should have been here. Okay, is equal to delta F, that is incremental force. So, the objective is to solve this equation for incremental displacements. Every time step, what is the displacement that is taking place in the system, because we are trying to study the motion of the granular system, right. Suppose if you have to solve this equation for a large system of simultaneous equations in FEM, it requires large computational power, and for a 3D system typically with 1000 particles, your stiffness matrix could be few million by a few million. So, it could be very large stiffness matrix. The most DEM approaches, what they use is an explicit approach, a little different from what was suggested by Kandal and Strack, but in philosophy it is more or less very similar. We try to avoid solving the global system of equations, rather we will look at the dynamic equilibrium of individual particles. So, we actually solve the Newton's second law of motion on individual particles, and as a result we need not store large global stiffness matrix as in FEM. But so you also should understand that we should also understand that this DEM also takes significant amount of computational power, not in terms of memory typically, but the amount of computation that it requires in terms of monitoring the contact detection and so on. So, the governing equation for our dynamical equilibrium of a particle goes like that. So, mu double dot, so that means each particle, mass of the particle and the acceleration of the particle is equal to some force. So, here you have various components of the forces. So, what we are seeing here is the first force here is the contact force. That means, let us say if a particle P is coming in contact with particle C, then there is a contact force between these two particles, isn't it? So, that is the contact force contribution. That means, because of the fact that particle P is in contact with particle C exerts some force on particle P. So, that is one sort of a force that acts on particle P. Next, you may also have a situation where the force is acting on the particle not due to contact, but because of some other reasons. These are called non-contact forces, such as cohesion forces and so on, right. That means that depends on the proximity of this particle to another particle, but they are not actually touching each other. But the fact that they are in the proximity of the another particle, there is some sort of a, for example, van der Waals interaction between the particles. Because of the van der Waals interaction, there may be a force exerted by particle J on particle P in here. So, that is what we call non-contact force. And the third one, if the particle is in a fluid medium, for example, the fluid force, the drag force exerted by the fluid on the particle is another source that can be there. And then you have gravity force. That means the particle is under the action of the gravity, and then the gravitational force will be there on the particle. So, that is the gravity force. In addition to all of them, you might be actually applying a force on the particle, external force. So, this is the applied force. So, most of the forces that we want to include in the system, either they go through non-contact forces or any other, and if some force is not mentioned here, suppose if you are solving a problem in which a new kind of force is coming into picture, then you can simply add that force. So, each particle is now subjected to various kinds of forces. Now, mu double dot is equal to sum total of all these forces, and now you need to solve that differential equation. That is as simple as that, right. Third one is a fluid force, because if the particle is in a fluid medium, the fluid will exert a drag force on the particle, right. So, that drag force is what we are calling fluid, because it is not, because the second one is a non-contact force due to the proximity of a particle with some other particle. If it is at a certain distance only, this will exert force. If it is far away, it will not exert force. For example, if you consider van der Waals forces of interaction, then the van der Waals force depends on the distance between the particles. If the distance particle is far away, there is no van der Waals force, but the particle is very close, and depending on other conditions being right, then there may be a van der Waals force of interaction. This van der Waals force of interaction does not require the particles to be touching each other. So, that is why it is called non-contact force. Okay? So, this is typically what we would see in systems like where you have particle size is very small. For example, pharmaceutical powders, additive manufacturing, wherein the particle size is few microns. So, then van der Waals forces of interactions become more and more prominent, because their values, because of the very small size in particles, the surface interactions become more important. So, then you need to take that into consideration, otherwise you will not. Okay? So, that is what actually I have explained whatever is there. So, fluid interaction force on particle P and non-contact force between particle P and other particles such as capillary forces, adhesive forces and so on. Okay? And then that is for linear. Yes?
Adhesive force is a contact force?
No, non-contact force. This is non-contact force. This is a non-contact force. So, we in principle you have to add if the material. So, for example, what we are talking about here, what are we talking about? We are talking about a particle. So, the contact force coming from the particle will have all the damping and everything that has to be embedded there, right. And when you, in addition to that, for your simulation to converge, you might have to add some artificial damping, something called numerical damping, for your equations to do a meaningful. That means they should stabilize within the reasonable time. Okay. And that is what about your linear terms, but you also have angular displacements. As a result, you have angular velocity and angular acceleration. So, this fellow is your mass moment of inertia, and this guy is angular velocity, the derivative of that is your angular acceleration, and this is sum total of all the moments acting on the particle, okay, by contact force on particle P and the number of moment transmitting contact forces, right. So, you solve these two things together to get your 6 degrees of freedom, that is acceleration, 3 linear accelerations and 3 rotational acceleration, angular accelerations, 3 linear velocities, angular velocities, linear displacements and angular displacements. So, basically what we do is, so you integrate it once, you get velocity, then integrate twice, then you get displacement. If you take a particular particle, right, so the particle may be in a fluid medium. So, imagine this is the scenario. Okay. Now, I am applying a force here, all right. So, because of this applied force, these particles are moving, that is true. But now, if I take this particle, if I isolate that particle, this particle is subjected to this force, and there is a contact force from this fellow, contact force from this fellow, and possibly contact force from this fellow. If it is under gravity, there is a gravitational force. If it is under fluid medium, there is a fluid drag force, all these things. But whereas if you take this particle, there is no applied force, there is only contact force that is happening. That means the boundary forces coming onto the particles are coming as applied force. For all other particles, wherever there is a externally applied force in addition to the contact forces, there only you will have applied force, otherwise other particles it will be 0. You are right here. Double dot is acceleration. Yes. So, sorry, I did not mention that. U is displacement, u dot is velocity, u double dot is acceleration. So, when we are trying to solve this set of equations, so during deformation in a granular material, what happens is the particle positions change continuously, right? That means you need to imagine you are compressing the system, or you are doing something and the particles are moving around. So, you need to understand how these particles are moving around, and hence you need to discretize your time, total time, into small time steps, and then try to see within that time, small time window, what happened. How did the particle A move from a position X to position Y, right? So, that is the reason why the DEM simulations are discretized in time discretized DEM simulations, where the system is examined at specific points in time. And what you should keep in mind is that, suppose if you are examining the assembly at time t is equal to 1 and time t equal to 2. What you are actually doing is, by knowing what has happened at time instant t, t equal to 1 and t equal to 0, you are trying to estimate what is going to happen at time t equal to 2, right? And then you will have the information about the system at time t equal to 2. But what you will not have is what is the state of the system, say at time t equal to 1.2. If you want to get the state of the system at time t equal to 1.2, you actually have to estimate what it is going. So, that means you need to solve the equations at time t equal to 1.2. So, that is why, depending upon the granularity of the data that you are interested in, you need to do the discretization accordingly. If you do not do that discretization, you do not have access to that information. Okay? And as a result, you might sometimes miss important dynamics of the system. So, for example, let us say if you have a particle here and a particle there. At this instance, they are not touching, okay? And this guy has a direction of, this guy has a direction of velocity this way, and this guy has a direction of velocity this way. If your delta t is sufficiently large, right? So, if you have velocity this much, what will be the displacement in a delta t? V times delta t, right? If this distance is larger than this distance, if the value of V delta t is larger than this distance, for this particle, what will happen? In the next time step, you will see this particle here, correct? But in reality, will it happen? In reality, it cannot happen, because this particle is going to stop it. So, unless you take this delta t to be sufficiently small, you will not be able to resolve the dynamics accurately. Then you are missing interaction between the particles, because it is an explicit step. So, you freeze the system at a specific time, and then you take a delta t and then find out what is going to be the position. And between, you are not doing anything. Unless you do this very small time stepping, you will not be able to understand or get the dynamics properly. Okay? So, that is one of the important considerations when you are doing a DEM simulation. Your time step should be chosen carefully. So, at each time step, so if you are frozen the system at time t equal to 0, now at time t equal to t1 at which you are trying to evaluate, there are two calculations that will be done. What are those two calculations? You will calculate contact forces based on most recently updated particle positions. So, because you are frozen at this point position, based on at that instance, based on the positions of the particles, you may have some particles having interpenetration, some particles may not be having interpenetration. All these particles you will look at and then calculate the contact force. And then you also look at applied torques, if there is any moment that is applied. Okay? So, all you do these things, and then you will generate the equilibrium equations, two sets of them, that is, one is for translation, another is for rotation. And then you solve this ordinary differential equation, mu double dot is equal to F, and then get the accelerations. Or so here MP, AP is the acceleration of the particle at time t and force, and typically your mass matrix in 2D, if you have two accelerations, it will be a lumped mass matrix. I do not want to get into how you create a lumped mass matrix and a consistent mass matrix. That's something that you probably have learnt in your dynamics course, but precisely you will solve that. But then how do you find velocity? From this equation, it is pretty straightforward to get acceleration, isn't it? You just have to take this fellow this side. It is just that if it happens to be a matrix, you need to find the inverse of the matrix and multiply that. That's a different matter, but you can find the accelerations, right? And now, how do you find the velocity? So most DEM codes use different kinds of time integration. One of the most popular time integration technique that people use is velocity Verlet time integration. Okay? So this is here position Verlet, and so basically it is very similar to your central difference scheme when you want to find the integration. So if you know the acceleration at time t, you can calculate using central difference scheme what is the velocity of the particle at time t plus delta t by 2 by knowing what is delta t, and then you can calculate at from the previous equation. Sorry. Here m inverse fp, that is what is m inverse fp is plugged into ap, and then you get velocity of the particle at time t plus delta t by 2, right? That is pretty straightforward. And once you have the velocity, then you can find out the displacement, again a similar central difference scheme kind of a thing, and you will figure out what is the displacement at next time step. Okay? So for 2D DEM simulations, if you are only working with 2D DEM simulations, there is no coupling between 3 degrees of rotational freedom, but if it is non-linear 3-dimensional, then you may have some coupling that we need to worry, but right now let us not look into it. Okay? So the particle angular velocities, angular acceleration, from there you can calculate angular velocity, and then from there you can calculate angular displacements exactly the same way that we have done. Okay? And for non-spherical particles, this can be little tricky because then you need to rotate the particle orientation also, because you need to understand non-spherical spherical particle in whichever way it is rotated, it is the same. It is very symmetric at about any axis, right? Whereas if you are dealing with non-spherical particle, an ellipse which is oriented horizontally might actually become like that, right? Whereas for a circle it does not matter, whatever you rotate, it is still going to have same, it will be seen as same orientation. So in order to solve these things, so we use an explicit time integration scheme. What do we mean by an explicit time integration scheme? If you carefully look at this fellow, right? Acceleration. What is it telling you? In order to, if you know the acceleration, you can find out the velocity at time t plus delta t by 2, and the velocity at time t plus delta t by 2 depends only on the quantities that are already known, right? You can simply plug in and get the value. This is some sort of an explicit scheme. If it is an implicit scheme, you will also have quantities that are functions of t plus delta t by 2 or t plus delta t on the right hand side as well. Then that becomes a nonlinear equation, and then you need to iteratively solve. But for DEM, we will rely on an explicit time integration. Whenever you are dealing with explicit time integration, you have to ensure that your solution is stable. So how do we do that? In order to ensure that the solution is stable, you have to choose your time steps to be sufficiently small. Otherwise, you can show that the solution is going to be unstable. So there are guidelines on how to choose a sufficiently small time step, and if you are using any commercial tool, typically they will suggest, if you are giving a larger time step, the commercial tool based on the particle density and elastic modulus, the commercial tools will suggest, okay, your time step is going to be too large, so why don't you reduce your time step, okay? What kind of errors that can creep in our DEM simulation? Typically, if you are calculating x position of the particle at time t plus delta t, if you are writing the Taylor series expansion of that fellow, right? So what if you are expanding this guy until until nth term, and then you have order of n plus 1 terms. If you only consider up to here, then there is some value that is left out as a truncation error. That means you are not considering that. Now what happens if you are only, so for example, if you look at the previous equation, we have only taken up to here, isn't it? We have not even taken this fellow. That means all this is going as truncation error, and that is the error that we may be making when you are estimating the new position. But now if you choose, why is that okay for us? Because if you are choosing delta t to be sufficiently small, then delta t square will become sufficiently small and all other terms will also be sufficiently small, and hence it is okay. Numerically it is not going to make a big difference, all right. So that is the reason why you have this delta t reduction that needs to be done, so as to ensure this truncation error. Now I won't say it will not be there, it becomes inconsequential. If the truncation error, no matter what you do, you will make some truncation error. But what you can say is that, okay, this truncation error, although it is there, it is not to be worried about, because you are taking delta t to be sufficiently small. Then you are anyway in your computation, you are only taking up to first order term. So that means if you are taking delta t to be larger, then the subsequent term, the ones that you have left out, also become magnitude wise comparable to the first part, right. If they become comparable to the first part, you cannot neglect them, right. So then your calculation will be wrong. Yeah, you change it delta t and then you see what is the difference between the first solution and second solution, and then you will realize after some time. So the way that if some of you are done mesh convergence in FEM, right, like mesh convergence is about the size of the element. Similarly, you can also do a convergence on the time step. So you choose different time steps. After some time the solution will not change. Further reducing time step further will not change the solution. Then whatever is the largest time step at which the solution stopped changing, that is what your meaningful delta t that you need to take. Okay. So for example, if you look at this picture, in this picture we are plotting axial strain versus normalized stress in a granular assembly. Okay. So this dashed line in the top that you are seeing, that is your theoretical peak, that means that is the theoretical limit, that is what is the actual solution. Now what you have done, you have solved the system using different delta t's. You can see delta t to be 0.75, very large time step, that is this fellow. It is oscillating about a point, but it is not stable, and 0.45 is this fellow. It is not oscillating, but it is actually giving you a different solution. And if you further reduce, 0.4 is somewhere here still oscillating, 0.35 is better, you can see 0.35 is doing a better job, and 0.05, 0.4 is oscillating, and 0.35 and 0.05 are stable. 0.4 is oscillating, this oscillating one is 0.4, and 0.05 and 0.35 are doing reasonably well. So which time step will you take? Will you take 0.05 or 0.35 for your simulation? 0.35 you should take. Why? Because 0.35 and 0.05 are not having any difference. So it doesn't make sense to take 0.05, you will run your simulation with 0.35. So this is typically demonstrating how time step can influence your simulation. So the general guidelines for choosing your time step is this: pi by 5 root m by k. So if you take a particle whose stiffness is k and m is its mass, so root k by m is the velocity in the elastic wave velocity within the particle, right, that is what it represents. So the delta t critical time step will be this. So your time step at any point cannot be larger than this. If your mass of the particle and stiffness of the particle is known, it cannot be larger than this, because the Rayleigh wave velocity of an elastic material depends on g and rho or m and k, right. And typically if you are having an Hertzian contact model, if your interaction between the particles, I told you about contact constitutive response, right, between two particles, how your contact force is calculated. If that constitutive model happens to be Hertzian contact model, then the delta t critical should be this. That means your delta t cannot be larger than this. where r is the r min. R min means smallest particle radius. Rho is the density, g is the shear modulus, alpha is a function of Poisson's ratio. Okay. So, typically what people do is they choose their delta t to be around 1/5 or 1/10 of the delta t critical, just to be safe. Okay. It is about particle, no, it is not here, that is why this is the general guideline, this is what you need to take. G is your shear modulus of the particle. The particle contact that has smallest g value, or particle having smallest g value. So, if you have particles of different material types, you look at the smallest g and the particle of smallest radius. So, that means r min times g combination or rho, this quantity whichever is the minimum, that is what you have to take, and that will be your delta T critical, because you have to account for the worst case scenario. The worst case scenario will be the value of r square root rho g, whichever is minimum within the assembly, that is what you need to take. If the contact model is different, then this equation may change, but it will not change significantly. Okay. Because it is dependent on r min and g are coming from the Hedgian contact model, but for each model you can, it will be more, the model's behavior more or less will be similar to this, because here the contact stiffness we are talking about. Because we are taking Hedgian contact model, the contact stiffness, the dependence of contact stiffness on radius and elastic modulus will be in one way. If you are taking JKR model, the dependence will be different. The idea is you have to take the stiffness of the contact. Okay. So, the critical time step that we are talking about, it is a function of the spring stiffness, particle density, number of contacts, current tangential stiffness in the case of variable stiffness in non-linear contact law, right. Individual particle density will not change. You are talking about assembly density. It does not depend on assembly density. We are only talking about individual particle here. Okay. The particle density will not change, it is a fundamental material property. We are not talking about, when we are talking about soil, we are actually talking about soil particle. So, soil particle density is what I am talking about. So, the density of the soil particle will not change, but the soil assembly will change when you are compacting, because the gaps are changing. Right? So, that is about explicit time step, and implicit time step algorithm if you take, they will be, you need not worry about the stability of the solution. That means it is actually unconditionally stable, but the problem is they take lot of time for convergence, and hence probably people have tried this, and for DEM simulations, because of so many non-linearities involved at the contact level, explicit time stepping is one of the is the method that happens to be successfully implemented over the years. Okay, so I think this part I will skip, because this is not something that I would like to talk about. Yes, we need to talk about damping in DEM simulations. So, when you are talking about pure elastic contact, such as Hedgian contact models, they do not account for energy dissipation in the physical system. So, when you are talking about yielding, the plastic dissipation, we actually talk about rupture of contact spring in normal direction or initiation of the interparticle frictional sliding in the tangential direction. So, and of course, we know that in reality the particle surfaces undergo asperity, plasticity and damage. So, particle surfaces in reality at very high local contact force, because the locally particles have some roughness, right, and at that roughness level, because the contact force is going to be extremely high, and as a result they may undergo plastic deformation. So, if although you are thinking that I am modeling it as completely elastic material, my contact interaction is only elastic, but reality is that there will be some plasticity at the local level, right, and hence complete elastic models are very unrealistic, although they are good for us to implement and show. So, the particles typically in a DEM setup, when you have only elastic interaction, they keep vibrating if there is no damping in it. What is the meaning of that? Because you are applying certain force, it's a dynamical system, it keeps oscillating, right, between the displacements. But unless you have a damping introduced into the system, there will not be any dissipation of energy, right. And hence, in order to account, although you are using purely elastic contact without any plasticity possible, what we will do is we will introduce some sort of an artificial damping into the system. Okay? So, that artificial damping will sort of mimic the physical behavior of the system. So, that artificial damping is what we call a numerical damping in several DEM simulations. So, here this guy shows what happens, linear elastic, this is a linear elastic response, this is a non-linear elastic response, and the other one is elastoplastic response, and so on. So, that here we can see that some sort of a damping taking place when you have the plastic numerical damping incorporated in the system. So, here your equation will change depending upon the type of damping that you are using, whether you are using non-viscous damping or mass proportional damping. So, you will add the damping term Cv dot, where C can be proportional to mass through a constant alpha. This is what we call mass proportional damping, and again you know what is the damping coefficient, and once you plug in, your equations can now be solved again using the integration schemes that we have discussed. So, when you are dealing with pure elastic contact, right, so you are not really talking about dissipation of energy in the material, right. If you are only talking about pure elastic contact, there is no dissipation that you can put in the contact constitutive law. However, in reality what happens, if you have a particle, although we are saying these are, I am only modeling two spherical particles, we are thinking that they are atomically smooth, but when you zoom in, the surfaces look like that, and when this surface is interacting with this surface, the local contact area is very small. So, although your force is same, force by area will be very high because the area is small, and as a result the stress, local stress may reach the yield strength of the material, and hence there will always be some local plastic deformation. That is something that we are not accounting for when you are doing pure elastic contact constitutive law. So, what is the way out? The way out is you introduce some numerical damping in the system to sort of account for or mimic such such energy dissipation systems in the DEM simulation. Okay, so now if you want to model damping explicitly, there are ways. There are two ways, that is, one is a mass damping and a non-viscous damping. If you are looking at mass damping, what do I mean by that is your damping coefficient is proportional to the mass of the system, right, and the dashpot, that means the C is a dashpot, isn't it, a spring dashpot system. So, dashpot connecting to each particle is accounted for through this, that guy represents the damping between the particle contact. And if you are using non-viscous damping, so which is another alternative to mass proportional damping, so what it actually does is it tries to look at the out of balance force, and damping will be proportional to that out of balance force. So, the damping force in this guy is given by minus alpha star Fp sine of Vp. Vp is the velocity of the particle. So, Fp is your resultant out of balance force on the particle, and corresponding to whatever is the, so that means what it does is, if you solve the system of equation, you take the free body diagram of the particle and you can calculate what is the out of balance force, and in the direction opposite to that out of balance force you will apply a damping force, right, and this alpha is your damping coefficient. So, this is what we call a non-viscous damping. You are not applying through a viscous dashpot, but it is simply you look at the out of balance force and apply opposite to the direction of the motion of the particle. So, this is how your system damping you can see is a non-viscous damping, how it is dying out, and then a mass proportional damping, how it is dying out, and so on. So, as I told you, the velocity Verlet algorithm is the most popular algorithm for time integration, And there are also other possible algorithms like predictor character methods and so on. These are different integration algorithms to solve your system of equations, but that is typically various numerical techniques to find out the solution, as simple as that. And now let us look at different contact force models. As I told you, in a typical DEM simulation, you have two stages. One is contact detection, contact resolution. These are very important in any DEM simulation. So what do we mean by contact detection? You need to identify, you take a particle and identify this particle is in contact with which particle. That means you need to develop something called a neighbor list. Some of you who are familiar with finite element modeling, you have element connectivity list, right? You generate an element connectivity list telling you that, okay, element 1 is connected by nodes 1, 2, 3, 4. Element 2 is connected by nodes 3, 5, 7, 6. We developed such a list, right? Similarly, here for each particle you write a neighbor list. So what are the particles that is it in contact with? But this neighbor list gets updated at each and every time step. So at each and every time step you need to find out this neighbor list. So to generate such neighbor list you need efficient algorithm, because at each and every time step you need to search in your domain a particle X is in contact with which other particle. Ideally, not ideally, in general. So if you have 1000 particles, general guideline is you have to check whether particle 1 is in contact with how many, which other particle amongst the 999 particles. So but that is very expensive, right? Time consuming. You have to one particle, you have to search, check with each and every, you have to run a loop over all the 999 particles. Now you can develop smart algorithms. For example, you have an assembly like that. Now if I am trying to find out the neighbors of this fellow, right? Does it make sense for me, if I don't pay much attention, I would be checking whether this guy is in making contact with this fellow. Does it make sense? It does not make sense. So what is a smarter way? I can actually subdivide this into 4 and I will only search for the contacts of particles in this bin with only particles in this bin, and if the particle is on the boundary of the bin, then I will search in the neighbors of the boundary. But otherwise I don't need to search. For example, if I have made not 4 bins, so the contacts of particles in this bin are only searched here. I don't need to search in these bins, isn't it? So this kind of binning algorithms will improve your contact detection efficiency, and it's a very important step that one needs to take into consideration. Otherwise your time that is spent in a DEM simulation skyrockets. When you are actually making a comparison between one commercial software and other commercial softwares, some of them they don't make their code open to you. The reason for that is they may have a better algorithm for contact detection. That is why their algorithm may work faster than some other algorithm. It is their IP in some sense. Okay? Even today, the contact detection algorithms efficiency, people still work on improving the contact detection algorithms efficiency. For spherical particles, it is probably more or less closed, but for non-spherical particles, it is extremely complicated, particularly when you are dealing with non-convex particle. What do we mean by a non-convex particle? So typically in a convex particle, if your assembly has convex particle, a particle will make only one contact with another particle. That means if you take this particle and this particle, if particle 1 and 2 are in contact with each other, there can only be one contact between these two fellows. Now let us take a scenario of a particle like that. This is the particle 3. These two are convex and this is non-convex. So if this particle 1 is making in contact with particle 3, if it is making a contact here, then there is only one contact that can be made. But let us imagine a scenario where this particle is making a contact here. So when you are doing contact detection, if your detection algorithm identifies that this particle is making contact here, you cannot stop searching whether this guy is making contact anywhere else with this particle, because it's a non-convex particle. So here it may be doing 2. What if this particle is not like that, like that? So it need not make 1, 2, but it can make as many number of contacts as possible with that one particle. So the contact detection algorithm for a non-convex particle is going to be much more complex than a convex particle. And contact resolution, that is the next important step, is the contact resolution, in which you actually compute the contact forces acting on a particle. So in order to do that, you need to pay attention to the contact geometry. How is the contact geometry evolving? So accurate calculation of contact geometry and contact kinematics is extremely important. All right? And yeah, then you need to also pay attention to what is the overlap between the particles, what is the separation between the particles, and relative tangential motion, what is it? Because if you want to have a normal contact and a tangential contact, right? In normal contact, you will have a spring between these two, and depending upon the distance between them, the spring could be a linear spring or non-linear spring, but you can find out. But if you take, you can also have a tangential spring and tangential dashpot. That means the particles may be sliding past each other, right? And but the particles, when they are sliding past each other, there are two things. One is they have a tangential spring, and there is also a friction, right? So your tangential force cannot be unbounded, because it is limited by the frictional force. Once you are able to overcome the frictional force, right, then you need to see what is the tangential interaction that is taking place between the particles. So in any DEM simulation, the sequence of operations leading to contact force calculation, which involves contact detection and contact resolution, will be about 90% of the simulation time. Yeah, it takes about 90% of the simulation time. And with increasing packing fraction, what I define what is the packing fraction? With increasing packing fraction and number of contacts increase, and hence your contact detection and resolution time also increases. What do we mean by that? So when your granular assembly is coming closer and closer, the number of contacts that a particle makes with others will increase, and hence your detection requires to identify those many contacts and then compute the contact forces, right? So if you have a simple analytical formula to calculate the contact force, that will reduce the time. But if your the formula to calculate the contact force itself requires you to solve some equation, then imagine how many equations you need to solve every time if you have to compute a contact force by solving another set of equations, right? In a contact force idealization, you have a normal force and tangential force. Typically, this normal force and tangential force are decoupled, meaning the normal force interactions will not affect the tangential force and so on. And you have two orthogonal rheological models to describe the contact forces. You use the rheological model, meaning you use springs, sliders and dashpots in order to describe the contact interaction between the particles. So spring we understand, dashpot we understand. What is a slider? A slider, in the case of normal direction, contact normal direction helps to prevent or limit the tensile forces between the particles. That means when the particles are compressing, there is no problem. Suppose if you want to define the cohesion force between the particles. So when you are separating the particles, what will happen? There will still be some resistance offered by the particles to separation, isn't it? But once that particles have moved sufficiently far away, then there should not be any resistance, right? So there you are defining a slider like thing. So this is the limit. The moment you will have interaction between the particles, as long as the sliders are close to each other, once the sliders move away, there is no interaction. That means you will cut the interaction after some time, which basically means if you have two particles which are very close, then there is, when you are separating them out, when you are pushing them, there is a contact force that comes in, but when you are separating them out, you say that there is no resistance. So when you are separating them out, what happens is there will be some, again even during separation there will be a spring, but this will not be a spring, this will be a slider, and after some time the slider will be broken. That means to say that the cohesion force is only applied up to that level, after that it is not there. That is true, but when you are writing the rheological model, that means here when I say decoupled, I am talking about the spring in the tangential direction. So when you are doing Hessian contact, your mu times Fn is the limiting force. Before that, you will have your tangential force will be maximum of mu times Fn and the tangential spring stiffness coming from the tangential spring stiffness. So the tangential force there depends on the normal force, but if you are only talking about the rheological model, that means only the springs, this spring and this spring are independent. The stiffness of the tangential spring and this spring are independent, but this tangential spring cannot have continuously increasing force as the normal force, because it will be capped at mu times Fn. The cap will happen at mu times Fn. Until then, it will be changing. Okay? So that is what it is. If you look at the normal force, it will continue to increase in the, if it is having a cohesion, particles are separating, right? When the particles are separating up to certain separation, there will be resistance. After that, there is no resistance. That means the bond strength is reached and then the force will be 0. That is in the tensile regime. But in the compressive regime, there is no such end. It continues to increase if it is a linear contact interaction. Is that clear? This is a normal interaction. Now coming to the shear strength, right? You will have cumulative tangential displacement and it is capped here at the shear. This is your mu times Fn plus cohesion. If you have mu times Fn plus cohesion, mu times Fn will be limited here. Let us say in the tangential direction there is no cohesion, the particle will not go in that direction. It will behave like that. The tangential contact interaction will be described by this line and then it will be capped here. Okay? But if you have cohesion, then it may be having a shear bond strength. But if you don't have, imagine there is no cohesion, this part is not mu times Fn, isn't it? Right? This is a limiting force. So you know we have discussed how a normal contact interaction is calculated in the previous class. So I am not going to get into that. So now linear elasticity based contact response, so one of the contact models, which is what we call Hedge-Mindlin contact model, or Hedgian, which is essentially based on Hedgian contact mechanics, which basically assumes both the contacting particles are linear elastic materials. There is no plasticity whatsoever, both the contacting particles. So it assumes initially a point contact before anything happens. First the particles will have a point contact and slowly with the application of the force, the contact area grows. So evolution of growth of the contact area, but during the entire period, the contacting bodies are still linear elastic in nature, which means we can only apply this when the contact area is sufficiently small. That is the meaning of that. And each contacting body is an elastic half space and contact area is elliptical in shape in general, and the surface properties of particles assume no asperities, right? The model itself does not account for any asperities, it is mathematically smooth surface, and the spheres are frictionless. That is why you need to add a separate frictional element in your contact model. These guys don't assume friction, and as I told you, contact area is relatively small and strains are small, otherwise the contact area will become large, and no interaction outside the loaded area, meaning if you have two particles, the interaction is only limited here. There is no interaction between these particles here and here. The interaction is only here. That means there cannot be any cohesive interaction between this side and this side. All the interactions are only local to that area, because two spheres, when they are coming in contact, or two spherical particles, they are coming in contact, that is what you will see, right? It's just the geometry. If you take two spheres and then take the contact area, that will in general be, or two ellipses, in general that will be an elliptic domain. So Hedgian contacts, it will now let us look at two spheres, let us say S1 and S2. You have something called an effective radius, effective particle radius, which is 1 over R1 plus 1 over R2, and we define an effective elastic modulus, that is 1 over E star, is given by 1 minus nu1 square by E1 plus 1 minus nu2 square by E2, where nu1 and E1 are elastic modulus and Poisson's ratio of the particle 1 and vice versa. And here basically particle 1 and particle 2 need not be of same material or same geometry, same size, that is what it means. And if they are not of same size and same material, then R star and E star are effective radius and effective modulus are calculated like that. From there you can calculate the radius of the contact circle. Here if you have two spheres, then the contact area will be circular region, and the radius of that contact area can be calculated using this formula, wherein your Fn is the normal force applied on these particles. If the normal force applied on these particles is this, that is the radius of the contact area. From there you can calculate contact overlap delta. So the contact overlap is 9 Fn square by 16 R star E star square whole to the power 1 by 3. Now in a DEM simulation, what is that we know? We don't know Fn, we are required to calculate Fn. What we know is delta, that is our contact overlap. If I know my contact overlap, then I plug in, I will solve this Fn, I will solve for Fn. Fn will be square root of delta cube times 16 RE square divided by 9, right? So that is how I calculate, that is the meaning of calculating contact force. By looking at the position of the particles, I can calculate what is the overlap. What is the overlap between the two particles? That is center distance R1 plus R2 minus the center distance between the particle. If it is greater than 0, then you will have it. If it is less than 0, you will not compute, because less than 0 means, if it is less than 0, that means there is overlap. Greater than 0 means there is no contact, so you will not calculate. Yes. So basically what you are saying is then one can calculate maximum traction, meaning force per unit area, using this formula. I have not derived that, but one can derive this. Okay. So because of the fact that there is contact, their contact pressure will be generated, right? The contact pressure will be contact force divided by contact area. So contact force is that, and contact force area will be pi times R square, where R is the radius of the contact patch. If you do that, then you will get contact pressure. This is what is your contact pressure, and that contact pressure will have certain, so contact pressure will be maximum localized. So if you look at this fellow, so the maximum contact pressure will be is given by this, but this contact pressure at the contact zone will change from, so this, let us say this is my contact area, it will change from here to here. He is calculating the maximum contact area, the contact pressure. Okay. Here you have tangential overlap, which is connected to elastic tangential stiffness, and then from there you can calculate the tangential force. Using these relations, you will be able to compute the tangential force, which will also add as another contact force on the particle. So these are the basic rheological models. If it is a spring, linear spring. If it is a non-linear spring, that is how it will be. It is a viscous damper and it is a rigid perfectly plastic slider. And in the previous case, now the contact force that we have calculated, Fn, right? How do you calculate the stiffness of the spring? So here the relationship between overlap and the force. Is it a linear relation or non-linear relation? Is this relation linear or non-linear? The force and overlap relation? Non-linear. Had it been a linear spring, it would have been linear. The fact that this is non-linear, Hedgian contact by nature is a non-linear. So, we are actually using a non-linear spring to describe the contact interaction between two particles. What happens with a contact force, how one contact force is calculated for Hedgian system, but similarly there will be considerations for other systems, and we can calculate the contact forces based on the contact model that we are choosing. Okay. Now the boundary conditions, how do I apply boundary conditions? Again, the choice of the boundary conditions plays a very critical role. Typically in DEM, the displacement boundary conditions are specified by fixing the position of the particle, and the force boundary conditions are specified by forces on particles. So some key features that we use in a DEM simulation are walls. So there can be rigid walls, most of the times we will only rigid walls, or periodic boundaries. Sometimes we will have membrane boundaries, particularly when you are doing triaxial compression. What you need to ensure is that your hydrostatic stress is constant. As a result, your boundary membrane will move forward and backward. So you need to account for this membrane deformation, and similarly you may have some systems may have axis symmetry. You have to impose that and mixed boundary conditions. So if you look at this fellow, you have a rigid planar boundary condition and a rigid cylindrical boundary condition. You have a cylinder and you are applying the load. From the top you have a planar wall, but around it, it's a cylindrical wall. So you should be able to, so there are several commercial tools or even open source tools will come with these wall conditions, so that the particle will be knowing where there is a wall. And how do you model a wall? But we have only seen between contact interaction between a particle and a particle, right, before. But if there is a wall, how do we go about it? If it is a wall, then you can consider that as a particle with infinite radius. Then it will be a wall, right? And the wall geometry position is defined by whether it is a cylindrical wall or a planar wall. So the walls can be either curved or planar. So in several machinery, so for example, you are dealing with mixing of particles in a pharmaceutical industry. So the blades of the mixer are interacting with the particles, but the blades can be modeled as moving walls. They are rigid moving walls, and they are usually considered as rigid because the elastic stiffness of them is much larger than the powder particle stiffness, right. So that the rigid walls is one of the popular wall boundary condition when we are dealing with machinery interaction with particles. So these guys have no inertia. We don't consider movement of the wall, meaning because of the particle forces, movement of the wall means we will move the wall, but what happens when the particle is applying force on the wall, will it move? So you have to calculate and just move the particle, but you will not consider the inertia of the wall. That means the mass of the wall is not taken into consideration. It will be seen as simple spring and then you move it. Okay. And forces acting on a wall do not influence wall motion. That is the consideration. Typical DEM simulations, typically the interaction between walls are not considered. What do you mean by that? So if I have a wall here and I have a wall here, normally what happens? If these two are interacting, there will be resistance, right? But in DEM simulations, we don't consider them, right? And hence, in the previous picture, when I may define a wall to be larger, cutting across the cylinder. When I am moving, you may be thinking that what is happening with this particular guy when it is crossing this fellow boundary. There is no interaction of the wall with the wall. Okay? This can be seen as a piston now. You need not explicitly model piston. You can define a wall and that will be seen as a piston because wall interactions are not modeled. If you want to model them, then you need to couple FEM and DEM. And as I said, periodic boundary conditions. So if you want to define, if you want to study large systems, extremely large systems, but then the number of particles will be humongously large. So you cannot simulate such large systems. Then what you would do is you define a small RVE and define periodic boundary conditions. When I say periodic boundary condition, if you have a particle here, when the particle leaves the domain, it will not leave the domain completely. What it does is, it leaves from this end but exactly enters from this side. So the boundary are not actually there, it is an infinite boundary. So this allows us to simulate systems that are extremely large. However, this does not allow us to simulate the effect of presence of wall, because when there is a wall, what happens? The particle gets struck there. But here what happens? The particle exits this periodic wall and enters from this side. Similarly, if it is exiting from this side, it will enter from this side. So, but this is very useful when you are dealing with very large scale systems. Maybe another 15 minutes we will talk about some simulations and then try to interpret the results that are coming out of it. This picture I have already shown you. So here what we are saying is, you have a pebble assembly, okay, and then this is actually a periodic assembly. Say it is dealing with periodic boundary conditions, and then I am compressing them, let us say. So what we are interested in is, what is the stress strain response if the assembly is a monosize, binary and a polydisperse assembly? What happens if you are dealing with a crushable pebble assembly? But the crushable pebble assembly that I am talking about is different from what Professor Zhao has mentioned in yesterday's class. Okay? So now let us introduce some terminology. What is a binary pebble assembly? A binary pebble assembly is a pebble assembly or particle assembly with two different pebble sizes. Pebble here is a particle. Okay? And polydisperse means you have a particle size distribution, you have more than two sizes of the particle. Now I define an important macroscopic characterizing parameter for a granular assembly called packing factor. What is the packing factor? That is the total volume of the pebbles divided by the volume of the container. So when you are taking a container, if you are putting some particles in it, will it occupy the entire space, entire volume? Is it possible for us to fill the entire volume of a container with spherical particles? We cannot, right? There is a limit. There will always be some voids. But when you are compressing, what happens to this packing volume? Initially you put in some particles, and then when you are compressing it, the gaps will reduce, voids will reduce, right? So the packing fraction is total volume of the pebbles divided by the volume of the container. For a polydisperse assembly, suppose if you have a particle size Rp cube, so packing factor for a polydisperse assembly can be defined like this: 4 pi R cube n by 3V, that R cube can be defined by this. Okay? And we also have a normal contact force between particle and particle j. There are so many particles, right? Each particle will have a normal force with another particle. But one of the macroscopic quantifying parameters for a pebble assembly is what we call average normal contact force, which is Fn I comma j by number of contacts or coordination number times n, right? So what was your n here? The total number of particles in the assembly. And another one term is hydrostatic pressure, which is basically sigma ii by 3. What is sigma ii? Sigma 11 plus sigma 22 plus sigma 33. And we have seen how one can calculate sigma 11, sigma 22, sigma 33 using this homogenization, volume averaging technique. And then you can calculate this hydrostatic pressure, where this delta star is given by that. So these are all the macroscopic parameters that we are interested in. One is packing factor, coordination number, that is NC, average normal contact force, hydrostatic pressure. Okay? So depending upon the, in a polydisperse packing, you see this delta star. In a polydisperse packing, this is a length scale that we are introducing, which is interparameter of delta ij Fn by Fnij. And now let us look at a binary pebble assembly. What did we say about binary pebble assembly? Two particle sizes, that's all, right? So I am defining a parameter called R star, which I am calling it as radius ratio, which is the ratio of small particle to large particle, smaller particle and larger particle radius. And now I am defining V star, which is ratio of, that means these are all non-dimensional numbers. R star is a non-dimensional radius, V star is a non-dimensional volume fraction. That is, what do you mean by volume fraction of Vg. Vg is given by Ng, number of particles of larger size, times 4/3 pi rg cube. Vs is Ns 4/3 pi rs cube. Okay. So here I am showing you a simulation which is basically odometric compression of a periodic granular assembly, and I have shown you this figure yesterday or in the previous class, wherein here we are saying that it is loading. When you are unloading, it is not following the same path, isn't it? Why is it not following the same path? Because there is frictional dissipation in the material, and hence the unloading path will be different, and when it comes to zero stress, you always have a residual strain in the system. What is the meaning of that? If you are compressing the assembly to some extent, and if you are removing the load, the assembly will not go back to its original position, it will stop somewhere in between. So that means macroscopically, if you are seeing, there seems to be some plasticity in the system. What this plasticity is not at the individual particle level, but the plasticity is the assembly level. So here we have a scenario wherein, if you carefully observe, we have three systems. Here we are looking at low packing fraction, here medium packing fraction, and high packing fraction. What is the low packing fraction system? Meaning I am talking about 0.6339, 0.6341, 0.6348. Medium is 0.6373, 6377, 6386. High is 0.6400, 6417, and 6436. You might now question, what are you talking? You are talking about packing fraction variation at third digit and fourth digit, right? It turns out that even the small packing fraction variation is going to have a significant influence on response in your granular assembly, depending upon the choice of your parameters, right? So here we have an experimental data of a macroscopic granular assembly. For a low packing factor, it does not match well with the experimental data, whereas medium packing fraction, it seems to match reasonably well, and again high packing fraction, it does not. And if you look at carefully, the high packing fraction assembly, so is finding much stiffer behavior compared to experimental data, whereas the stiffness of the medium packing fraction assembly seems to be matching with the experimental data reasonably well. But does not mean much, because when it matches with the experimental data, am I happy? Why am I not happy? Yeah, because the packing fractions are different. So the actual packing fraction of the system is different, right? It is not, yeah, so it should not match for everything, right? If here the packing fraction here is different from what is the experimental packing fraction. Here probably it is closer, that is why it is matching. Am I happy? Should I be happy or should I be unhappy? So here, although I am saying it is monodisperse assembly, in reality, what is the experiment that I am doing? I am doing a uniaxial compression experiment. What is the simulation I am doing? It's a periodic assembly. I am not modeling the walls, isn't it? So although I am not modeling the walls, because I have taken my system size to be so small, here I have 5000 by 5, I have 5000 particles in this system. But in real system, you will have few thousands, or if not a million particles. So first of all, I don't have the boundary effect, and the second thing, my simulations assume atomically smooth surface, which it is not true in the reality. And the third thing, I don't know if my friction coefficient is same everywhere. In my entire assembly, friction between two particles is constant, but why should it be? It need not be, right? Because the particles compositions may be different. There are some variations despite that. So whenever I am doing my DEM simulation, I am not really interested so much in the quantitative comparison. If at all I get with a reasonable explanation, I am happy. But what am I interested? I am more interested in observing qualitative features, whether I am able to see certain qualitative features. So let us look at this fellow. Here it is very visible. You have a loading path and your unloading path is different from the loading path. Yes or no? The unloading path is different from the loading path. And there is some residual strain. because it is not going back here. There is some residual strain. Now if I look at this fellow, I have my red color, let us look at the red fellow, my red color guy going like that and unloading this way. They are following two different paths and I am observing a residual strain. Although the amount of residual strain that I have computed from my simulation is not matching with the experimental data. Experimental residual strain is here somewhere 0.25, whereas my simulation residual strain is larger. So here the idea is not really to compare bang one on one, but to see whether the physical features are matching or not. Okay? So now what we said was the loading and unloading paths are different, right? Why they are different? Because there is some frictional dissipation that is sitting in the material. Now here I have a binary assembly. Here I don't have an experimental data. Okay? Now what I said was my simulation is capturing the physics with a reasonable accuracy. Now I have a binary pebble assembly. One more thing I want to say. If my packing fraction is higher, this guy is going to be, response is going to be stiffer. Is it expected or not? My system should show higher stiffness when my packing fraction is higher, because there will be more resistance to the deformation. Fine. Now let us look at this fellow. I am dealing with one particular binary assembly whose radius ratio is 0.6 and volume fraction ratio is 0.7, normalized radius and normalized volume fraction. Some thing I have taken. Now this is 0.66 packing fraction, 0.65 and 0.643. So I would expect this is the increasing packing fraction and hence this will have lower slope which is expected, and the residual strain again is dependent on the packing fraction. If I have higher packing fraction, am I expecting more residual strain or less residual strain? Should the residual strain increase with respect to packing fraction or not? It should increase. If I have higher packing fraction, should I have more residual strain or less residual strain? It cannot rearrange that much and hence the frictional dissipation is less. Since the dissipation is less, it has to come back to its original configuration. That is the reason why all this guy is trying to come back to its original configuration, whereas the lower one is not able to come back to its original configuration, it has stopped here. Okay? So you have large residual strain for loosely packed assembly because there is lot of motion. It is not only friction. Friction is one aspect, but there is another aspect. The particle might be moving from one equilibrium position to another equilibrium position when during loading. When you are unloading, the particle which has moved from one equilibrium position to another equilibrium position may not have the driving force to go back to the previous equilibrium position, although there is no frictional dissipation. That is also a reason why the unloading path may not be the same. It is not only because of friction. Similarly, now let us look at the effect of R star. What is R star? Radius ratio. If R star is equal to 1, what is the meaning of that? Mono-size assembly. And if I am reducing R star, what is the meaning of that? There is a larger gap between particle sizes. There are large particles and small particles. You have it. Okay? Now, if you carefully observe, which one has the highest packing fraction? 0.649 is the highest packing fraction. What did we learn in the previous slide? If I have highest packing fraction, it should have higher stiffness. But what is happening now? That is the one that has the lowest stiffness. Why is that? The reason for that is, although the packing fraction is higher, because there is a particle size difference, these particles, small particles, can go and sit in the interstitials of the large particles. So if I have to give you one example, if I say I have a surface and I have a block, and the same surface, I am keeping the same block, but now I am keeping it on some rollers. Same block, exactly the same guy, I just drew it differently, but same block. Which one is easier to move? Huh? First one or second one? Second one is obvious, right? Yes or no? So now, when you have a large particles and small particles, these small particles amongst large particles will give you something called a ball bearing like effect. So although the overall packing fraction is large, these small particles sitting in the interstitials will act like a ball bearing like scenario, and hence overall stiffness of the system is reducing, because the motion is easier when you have different particle sizes. And that is the reason why you have although this guy has higher packing fraction, but that is the lowest stiffness. And as a result, of course, your residual strain is larger. So when you say your particle size variation is increased, then it becomes much easier for you to deform the material for a granular assembly compared to a mono size assembly. Everything else is same, only size fraction is different, but volume fraction V star is kept constant in all these scenarios. Now, you kept R star same now. Now you are changing the volume fraction. What is the meaning of that? There will be more V stars. So we will have stiffer response with large V star. What happens is small pebbles creating the ball bearing like effect, reducing the net stiffness. So with increasing V star, you are actually increasing the number of volume fraction of small pebbles. As a result, your ball bearing effect is pronounced. Again, although that has the highest stiffness, that has the highest packing fraction, that has the lowest stiffness. Okay, I have in this, there are 3 curves I got, no? There are 3 different guys. Now what I am doing? I talked about average normal contact force, isn't it? In all these 3 assemblies, I am monitoring my average normal contact force, and I have also calculated something called an average radius of the assembly. Because particles have 2 different radii, I am calculating an average radius also. If I normalize, if I find some sort of an average stress, F average by E R square, and if I plot that with the hydrostatic pressure of the system, interestingly what we see is that all these 3 curves collapse onto a single line. Now this is my master curve. What can I do with this? I can actually now use this curve to design my granular system. So irrespective of what is my V star, 0.2, 0.4, 0.7, irrespective of that, it is all falling under one curve. This is what we call a universal behavior, which can be used as a design guideline. So you have done a granular simulation, but then you got some macroscopic feature which is independent of the individual particle sizes. And if you look at this is again we call it the length scale effect, wherein you are talking about average coordination number for these 3 of them as a function of hydrostatic pressure, that changes. Although this is same, but this guy is changing based on the value of V star. Okay? And a similar thing is done for a polydisperse assembly. Again, for a polydisperse assembly, previously we have seen average coordination number showing different behavior, right? Now for a polydisperse assembly, we have a average normalized force, average normalized coordination number, NCP star. When we plot these things, again we have universal curves, so that you can use them as design guidelines. Okay, I think we will not have time for this thing, crushable pebble assembly. I will skip and we will stop here.